Okay, Ruzica, are you there?
I am here and I'm ready to share. Just a second.
Hello.
You can hear me and see me. And do you also see my slides?
Yes, I do.
Excellent then.
All right, so let's get started. It's my great pleasure to introduce Ruzica Piskac. Ruzica is an associate professor in the computer science department at Yale. She was previously an independent researcher at Max Planck Institute and completed her PhD from EPFL in 2011. She has won many awards for her work, including an NSF Career Award, a Facebook Communications and Networking Award, and Microsoft Research Award for Software Engineering Innovation Foundations. So without further ado, Ruzica.
Thank you very much, and thank you for inviting me. Thank you, Albert. So this talk full title is Using Set Solvers to Prevent failures in the cloud. But if you look what is then follow-up is an application talk. When Albert reached out to me and asked me if I could give this additional talk on Friday, he asked me whether that could be a talk where we talk a little bit about applications of set solving. And while when Vijay was mentioning, he mentioned those awards that are kind of very applicable, like networking, like this one, or software engineering. I do consider myself a person who is working in, like developing new decision procedures. But nevertheless, I'm really excited about that work because what you will see now is a joint work with Enan, who used at that time be my postdoc, but now he's doing really great at Alibaba Research. And that is a really great example, in my opinion, of how set solvers can help to solve a very, very problematic, very like untrackable problem in the industry. So if previous talks were like showing how powerful hammers we have, this one will be more about showing nails. And Enan I'm really happy that he found the time in his busy schedule so that he can, at the end, step in and tell us more about real world data, the data which he works every day, and then also maybe give an outline of problems that are out there in industry. So hopefully that will also be motivation that we start to talk to each other, because, like if I, who is not even a set developer, could come up with such a nice improvement, I'm pretty sure that all of you guys, you will give enhanced tools that he will be able to improve a couple of thousand times. So without advertisement, let me actually go to a talk. And we all use cloud today, right? Even this talk, I see it's recorded, will be on the cloud, and all our data are on the cloud. And we somehow rely on the fact that our data is always there, that if we need our data, we just will always be able to access that. But then, of course, question is this really the case? And now, to motivate our research, let me start with a very, very, very simplified version of the cloud. You have see here a couple of servers, and let's assume you replicated this data over 3 different servers. 3 different servers, well, on the surface, they are not really, maybe they have connected through several switches, but still, nevertheless, there are a couple of switches. They're not really so much dependent, and we assume our data is available all the time. Now, if you look at a little bit closer, you will see that if this router dies, then also the other 2 switches that are connecting to this router will die, and we won't be able to access our data. So then now this is a simple problem, and you can say whether this really happens in the practice. I mean, but the fact is, it indeed does. So what you see here, what I showed you, this very simple example, is just mimicking a problem that has happened at Amazon Web Service. When I remember that because that was approximately the time when I came to the States and everyone was very upset. People could not access their Facebook. There was lots of complaint. But I don't want to just trash Amazon. I want to also show like the problems like this, we can constantly read about them, and they are just some sorts of copy pastes from from existing news. And now, of course, when a problem like this appears, it will capture the eye of a systems community. And there were many approaches that were working in that direction, where they actually say, okay, if in summary, they have all the time the same theme. If failure like this has happened, let's do troubleshoot the system. Let's see what has happened so that we can solve problem after the outage occurs. And of course, now you can think about it. That means longer system downtime, well prolonged recovery, and we are all now in pandemic, so we know that cure is actually, it's much better that we don't come to the phase that we need to cure something, that we actually will rather be in the phase that we want to prevent disease instead of trying to cure that. And this was exactly the work that when Anand was at Yale started to work on. So what he did was he developed his first approach towards solving that problem. So I will describe that system, which he called INDAS, and that was the first system that was addressing this problem. And then we started to chat. We were actually similar, same building, same floor. So we started to talk and see whether there is a similar, whether there is a better solution. And I guess to this audience, I really don't need to sell one should use set solvers, but you will see how nicely and easily we could model this problem that you see using set solvers. So that will be, as I said, it's really application talk. And then after that, Anand will tell you how to take this, apply it to the real world cloud, and tell you more about the problems that are out there in community. And hopefully you will then also all after that start to talk to him and bring even more problems. So now let me now start first with this project called INDAS. As you can see, it was a project published at OSDI. So this is again another system conference. And what was INDAS doing? Actually, it worked in a couple of steps. The first one is it would collect all the data about network. And then once he would have that, all this data, who is connected, how is connected, who relies on what, then actually all this data would be used to model something that is called fault graph. Now, some of you might say like, oh, fault graph, like in MinCatSet, exactly in such type of fault graph. And then we need it once we have a fault graph, and he's saying like, okay, what will have to happen that, like that the system crashes, then we actually will have to find all these configurations that are causing the system to crash. So now let me start to give you an overview how it was working. Like first part is pretty, would probably belong to some networking conference. So we'll just kind of give you some details, but it's not that much set related. So we actually reused existing tools. So there is a tool, if you look at the example here, very simple network, there is a tool called NSD Miner, and the tool would actually scan network and derive all the data in the following form, where you will have, for example, here I have source, that's server 1, then I have it's connected via internet, it can reach core 1, and all the data were actually collected by this tool called NSD Miner, and they were given to us, and it would be stored in the database. Now, once we had this relational description of the problem, then we immediately could go to the next step, which was, let's build this dependency. So let's recall again our initial replication system that we had, like you put things on the couple of servers, and even easier, let's assume you only put things to 2 servers. So you know that your configuration, your replicating system will fail. You won't be able to access your data if every single of your servers fails, right? I will have server 1 will fail, and notice, and also server 2 will fail. So, okay, that's kind of reasonable that you can assume if all of them fails, then I know that I cannot access my data. However, now let's look into the servers. So when server 1 will fail, well, it will fail if its hardware fails. Or now notice it's not actually, we don't even put and anymore. Now it's enough that one of those things fails. If hardware will fail, or its network access will fail, or its software will fail, and so on. I mean, and we can continue on, then we can look into while the network will fail. So all this was also, again, constructed automatically. First step was like analyze network using NSD miner, save it in this relational database, pull out and construct this graph, which will actually explains who depends on what and how. Now, if you look at this, so now we talk about Yang and An, who was at that time not still aware that formal methods are the best things in the world. So they tried to use something called min-cut solver, but as you probably know, this is the NP complete problem, well, the same like set solvers, but nevertheless, it wasn't really scaling pretty well. So what then they did, they said, well, you know, like we need to just get approximate feeling. So what they would do at every root, at every leaf, they would flip a coin, and then it would be either, then we would say either it fails or not. So now if we assume that it failed, then we will put this X, or we assume that it didn't fail, and practically based, you will immediately get one configuration saying like, if aggregation switch fails and aggregation switch two fails, and or they didn't fail, and when we propagate it, then we will know whether the main configuration fail or not. So now you can see this is the basis for Monte Carlo method, right? So they would repeat this process many, many times, and the more you will repeat, the more accurate description of the compositions that need to fail simultaneously, so that original deployment fails, you would achieve more and more of them. So now you can look at that and you will say, well, there are clearly several issues, right? One of them is that it is hard really to express diverse auditing task, right? We cannot ask, like, if we just say, like, will it fail, and find me this other parts which will fail, but you cannot ask maybe anything anymore. What is the minimal component, which is what min-cut set would answer, and those things you will not able to answer. So, I mean, sorry, I didn't say the others. The other one is like, it was really slow, you will see, based on the result that we will show at the end. And one of the things is like, you can just kind of pinpoint the problem. There was nothing to do that you solved the problem. So what we did, we started talking, then we said like, well, we should use set solvers for that. And we proposed engine, which is called, which we called rep auditing engine. And let me tell you what was the secret sauce. Like, we could develop a new domain specific auditing language that could easily express diverse auditing tasks. And that was pretty easy, because once we modeled everything as a set formula, then it was just like boiled down to find the minimal unsatisfiable core, add additional constraints, and it was constantly boiled down to solving constraints. And it was much faster. Well, thanks for everyone for developing a new and fast set solvers. And in addition, we described, outlined how the synthesis would work for this approach, how we would give a more, how we would not only be able to say, look, this will fail, but we would even give the user feedback. But if you change something, if you put it maybe on different server, then you will reduce your failure probability. So that's what we've done. Now let's, we go back to the problem that we started with. Again, simplified version. What does it mean? If we want to identify that this, I mean, observing just the picture, we can see that this router is problematic. If it dies, our whole replication system will die. But how it works, we more or less have this auditing problem where we will say, well, write down, I'm using server 1 and server 2, and can you rank me this, what we call risk graph component? And we would get, the user wouldn't need to do this, what is in the blue box. Well, what is in the blue box is a black box for user. What would user would get, user would just get the answer, which will say, well, you're looking at the risk components. Your most problematic is this core one. If it dies, you don't have access to your replication system, replicated data, but also you will, is the same if aggregation switch 1 and 2 die at the same time, you are in the same trouble. So if you look what was behind that, we were using, again, all things that I described. That's why I spent so much time talking about this fault graph. Then we would convert this into CNF form and use weighted vector solvers. Now, I don't don't want to go so much into auditing language and all the auditing details. Maybe just to tell you interesting concepts. Remember, I was complaining that we didn't have enough expressibility with this old approach. So now what we can do, we can say, let me rank the components, let me rank the devices which are most likely to fail. What is exactly if I develop a certain if I care only about one replication system, what is the failure probability? Can you give me some recommendations? So all this is now in our language. And now to give you the semantics of this one, so a user can write properties like that, and how we envision it will work. Here is our database that already analyzed network. Here is our user rights auditing problem as the one as you have seen here, and then user will get, based on this network user and our auditing engine, which is actually again based on set solvers, user will get a report telling us more or less what is the failure probability or whatever we ask in our auditing problem. Now let me actually look more. I guess I promised to Albert application talk, so let me actually look into application, right? So first, I already mentioned several times risk groups in the fault graphs, and I guess name is pretty much self-descriptive. This is a group in the fault graph, such that if this group of the nodes fails, then we know that the root failure of a root node will happen. So here we look here that A2 is clearly one such a risk group, but also at the same time, A1 and A3 jointly are also risk group, because if A1 and A3 dies, then we know that both E1 and the second in one, which is actually E2, should die too, and then we know that we don't have our deployment. But if only A1 dies, that's fine, because if A1 dies, then E1, like left E1, won't be accessible, but the right one is still there, and we have access to our data. So now, looking at that, you can clearly see that this will take into account that we have AND and OR nodes. Clearly, we can encode all this as a formula, Boolean formula, and practically the problem boils down to find satisfying assignments to Boolean formula. So every satisfying assignment will represent a risk group. Now, you can also ask, do you have negations? Yes, we will do have negations, but we are getting there. So initially, it looks like we don't have them, but you can see. So now you can also look at the risk groups, and you say, well, if A2 and A3 dies, that's like bad, but it's much worse if A2 dies, because it's only one of them, right? So then the question is like whether all risk groups are created equal, and clearly not, because if they're smaller, like there is much less chance, there is much higher chance that only one thing will die, that 5 things will die simultaneously. Although we know how it's in life, probably 5 things will die simultaneously. But anyway, we need it not only to find what a typical problem would say, find me a solution, but find me maybe the best solution in that case. So we wanted to find top K minimal risk groups. And we looked into something which is called mean cost set problem. I don't actually look into chat. Are there any questions, or is everything clear so far? Everyone is with me?
Everything is clear.
Okay, perfect. Thank you very much then. If you have any questions, just please stop. So let me then go, let me go back to mean cost set problem, right? So you all know what is set problem, right? Set problem just means I have a set of variables and I want to find a solution. But there is, if each variable would also have a cost, so then you actually want to find a cost solution that costs the least money. So and if you'll ask now, how is this related to our size? Well, we can simply say, let's cost of each variable be 1. In that case, mean cost solution to the problem is indeed finding the solution of the minimal size. But then interestingly enough, once we started to model into that direction, then we realized, but it's not also, again, not only that all risk components are equal, also it's not the case that all devices are equal. Some devices are of really good quality, but some devices will constantly, like die. They have different failure probabilities. And now having, again, the same approach of min cost set problem, we could assign we could actually find risk component, which was not necessarily the smallest in the size, but looking into failure probabilities of each device, again, we could find the minimal failure probability. So now let's look maybe what would be here in when we've just focused on the size. You can see I'm saying each of the components has value 1. That means, like it will, like I want to just, like I want to just see the size. And in that case, I can easily find that my minimal component is actually exactly A2. Now, if I want to maybe put different components, let's say if I will say I have maybe failure probability of A1 is 10%, failure probability of A2 is 30%, and failure probability of A2 is 20%. So clearly those are pumped up numbers, but just for easier illustration, then you can simply say you will again additionally need to multiply, right? If A1 and A2 die at the same, A3 die at the same time, we will see that then failure probability is 0.002. And then again, using the same reasoning as before, we find that since this one has clearly the highest probability, we report that one. Now, you can now kind of notice that I already mentioned if A1 dies and A3 dies at the same time, I multiply those things, right? And if you look at the problem, it is not exactly what problem talks about. It's multiplication, it's addition. So let me show you a trick that we did. So how to reduce addition to multiplication, of course, using algorithms. And I should probably ask Anand if he still remembers the things, because what has happened was like, okay, like if we use algorithms, I'm really tired, I'm sorry. If we use logarithms, that means, like we can really reduce multiplication to addition. But then again, the problem was why we needed negative value was because if you look at logarithmic function, it goes like this, and we actually needed the other way. So that's why we use negative value. And we needed to multiply by 100 for simple reason, because the numbers we were getting were too small to actually compare. So this was just, let's multiply everything with 100 so that we can at least compare the values. So, and again, using, like these simple tricks, we were again in the same problem that we have min cost problem, and we again try to solve that. And how to find, now here comes where do come our negations. So far you have only seen and or, but how do we find top K critical risk groups? Maybe our solution was relatively naive, because what we did, we would find top solution, then we would negate that solution and repeat the process. So, like maybe there is something that we was like, oh, there is so much easier and more elegant solution. We would like to hear that from you. But with us, it was working pretty smooth, because I usually don't want to see top 30 things. Like it was just give me top 5 or top 3 to see what is the most at the risk at that time. And that's it, I guess. Now, one thing that is also that we were kind of very inspired by Kuldip's talk was computing the failure probability of the whole system. Because if you think about, now imagine we have our system and we create the graph, and I'm asking you, so what is overall failure probability if we already have those numbers? And there is how you ask that. Well, the failure probability will be more or less finding models. Like as we said, like each positive solution each satisfying assignment is corresponds to one failure event, which means that if we find how many models we have, we actually have found the overall failure probability of the system. So we didn't need to run our K-loop, but it was enough that we actually just do model counting, and then we divide with 2 to the n. Excuse me, there is a question or a... I don't see it. I see something.
Are you saying you did use this, or is this something you want to do as feature?
No, this is what we already did implement.
So, Ruzica, there is a question.
Sure.
What is the scale of this problem? How many variables are we?
We are getting there. We are getting there. I mean, you have to stay with us until the end. You
Yeah,
can't
it's not
just
okay.
put the number and run away.
Karem Sakala's question.
Yeah. So I will show this in like 2-3 slides. And then I will actually show you that how to work in even bigger things. So anyway, so where we are, what I also did, right. So we could use this failure probability with model counting only if we assume that all the boxes are equal, because in that case, if all the boxes are equal, then their failure probability is 0.5, like either it will fail or it won't, and then we could actually use model counters, right? However, if you remember when I showed you picture before here, each of them had a different probability. And then how, again, we did it was a little bit, like, again, maybe there is a smarter way, but for us, it was a trick that worked pretty neatly. What we did was, like, if it's already 1/2, then it's fine. Otherwise, we would just kind of, like, here was the trick was 1/8. 1/8 is we have to kind of introduce 3 fake nodes, which would actually, again, each of them have a probability 1/2. And then when you multiply failure probability of this whole node on the top, it is exactly 1/8. Now, in reality, like, you won't really get 1/8, you will get something 1/7, but then we would just do approximation, because also this failure probability of certain device, it's not like this is really precise. This is like estimated failure probability. So that's the trick that we use. And now, thank you for the question. Now we want to come how fast it is. And it is much faster. And, oh no, do I have time for repair? Maybe let me quickly go to tell you how fast it was, and then you can actually see. So like I already said, we had a first implementation, which was failure sampling. That was the work that Anand did as a part of his PhD studies. And so we really had an expert who knew how to write all these editing tasks. And this was the line of codes he needed to describe all these editing tasks. That was encoding problem using some minimal cut set solver. And this was just using our ArrayL language. And you can see the reason why we actually could do this well, because we already knew which problems arise in the practice. So all our components that we introduced were actually kind of tuned towards that we can easily express what system administrator wants to ask about a system. And at that time, we were young and naive, and we only had our system here called the at that time we could even still use in person student lab, where we could actually, and we could simulate various topologies. So we came with the topologies that would have 140 routers. So this is the number of switches and so on. So all these topologies were simulating using a tool, again, from networking that is used. You kind of provide parameters, and then you actually get a topology which corresponds to real life topology. So if you can see, at that time we actually even had topology C, which was not D, which was a bit bigger, but like then we really needed to wait for results to get out. But I know that Anand will tell you how he actually used this in the real world setting. So to go here, topology C has around 70,000 devices. And if you look how fast it was, let me actually show you. So when we were using min cut set algorithm, right? Because we used existing tools, I forgot the name, but it was super accurate, but it also took a little bit of time. We really needed, time to compute that. On these topology questions that we were asking. However, when you would use Indes, that was this Monte Carlo simulator, it was getting there. You can see after 10 rounds, you would actually get accuracy of around 20%. After a million rounds, you would get accuracy, 10 to the 5 million rounds, you would get accuracy of 30%. And after 10 to the 7 rounds, you're almost here in the time, but you're still with the accuracy of your answer, which is closely to 40%. So if you would kind of imagine here, line, you could really see exponential growth. Now, again, thank you all, guys, set solvers, developers. We really appreciate that, because when we ran all these tasks on the 70,000 nodes, we actually got around 300 times speed up. So we were like really happy with that. And I guess Enan wants to take over here, but if we will have a time, we will just kind of tell you more about repair. But Enan, since people wanted to see how things are working well, maybe, oh no, do you want to share, or do you want to talk?
Yeah, I can share my screen. Yeah.
Okay,
So,
thank you, Anand.
Thank you. Let me share my screen. So, yeah, good. So Aranka,
remember well the project, or?
Yeah. So So thank you very much for Ruzica's story. Yeah. So let's continue that. So after I left Yale, I joined the Alibaba Group. So I tried to deploy the RAP audit in Alibaba Group. The Alibaba is one of the largest cloud providers in this world. We are planning to, at the very beginning, we are just planning to use RAP audit to audit any update state in our service runtime, like shown in this picture. But this is because the majority of the big outages in our network were caused by the service updates, such as changing the network paths and upgrading the software component and dependencies. So our system is named the Cloud Canary. Well, it worked well, like what Ruzica just showed, but unfortunately, our operators asked us whether it could be more faster, because the number of our update tasks increased super fast. And in the most busy time, our operators actually need to commit one update task every 5 hours. So in addition, actually, because we are trying to target the industry scale services. So actually, we have, I'm sorry.
And on quick question, when you say update task, you mean upgrading software components under the cloud?
Yes, exactly. Yeah, so including both network and software. For example, you can say remove one link between the two switches and add another link between another two switches. This is one update, and another update might be we upgraded the version of a software from 1.0 to 2.0.
So just to reiterate, sorry, you were saying you had one update task per 5 hours. Is that what you were saying? That was the rate at which you're doing updates?
Right. So yeah.
Okay. Thank you.
So this is actually a great question. What I want to emphasize is update is very, very important for our operators, because we did a lot of updates every day. So update is dangerous. We need to prevent the problems resulting from the update. And so we are targeting the industry level services. So it contains hundreds of thousands of components. So I remember just a question about the scale of the data set. So because I'm not allowed to expose the absolute number of our components, but what I can say is actually we are targeting the components. The number of components is higher than 100,000 components. It's more than that, but I cannot expose the absolute number for that. I mean our real network, right? So and we have a new requirement, whether we can do fast. So how to address this problem? And because we're targeting much more components in the real scale, right? And we have a key insight because we are targeting the service update. So typically the service update, just change. They do not typically change too many components from the previous update snapshot. So we can just audit the differential parts between the previous and the updated snapshots instead of auditing the entire updated snapshot from scratch. So this is our key insight. And so with this key insight, we developed an algorithm for Cloud Canary, in which allows us to only audit the incremental parts with within an updated snapshot. And so we're now using rep audit for the initialization phase, like shown in this picture. And during the service runtime, we just run Cloud Canary to do the incremental auditing. And because so this algorithm actually is not trivial. Due to limited time, I cannot go through the detail, but I will show you the key insight about this algorithm, and you can read our paper for more details. This work was published in NSDI, which is a top network conference last year. So the key insight here is the triangles here mean the snapshot for the photograph. And the first thing is we analyze, we get the photograph. Yeah, and we found the border nodes. The border nodes means the black nodes in this photograph. And the border nodes are actually the root nodes for the updated sub photographs. And so after we found the border node, and we only need to use the size solver to identify the risk groups in the sub photographs. And after that, we also propose another algorithm to merge the result from top to from the bottom to up to get the final results. And this is very interesting algorithm. So if you are interested in that, just read our paper. And actually, during this process, we only audit the delta between the updates. So let me show some results. So this is a real results. We did this real deployment in our network. And from this picture, so the S1, 2, 3, 4 are the real update. So from this picture, we can observe that the interval between two updates are actually very fast. It's just a short time. And so we did a lot of updates in this service runtime. And if we use the existing work to try to do this audit, and they cannot finish the task on time, and because another update will come soon, right? And so if we use the Cloud Canary, because we only audit the data between the snapshots, so actually we can finish the auditing task on time. So this is the key thing happened in our real network. And
so in this Cloud Canary, that result that you're showing here, I have two questions here. One is the incrementality key to the fact that it's much faster than rep audit, or?
Can I say it again? What was?
I was wondering why Cloud Canary is so much better than.
Oh, because we only audit the data between the two snapshots, right? So the existing work actually, including the rep audit, they audit the entire photograph from scratch. Yeah, and because between the two updates, we actually only have the small part is updated. So what we need to do is just to analyze the data part, yeah, and get the final result. This is the key insight. Is that clear?
Mm-hmm. Yes. Yeah, makes sense.
Okay, thanks. Okay, so this is the real result here. We analyze our real cloud. So we have the following results from our the case study. So the microservice update sometimes introduce the common dependency. For example, the authentication component and access control system. So we observed some, say, access control list rule, which might be the common dependency. So if that rule is wrong or it's incorrect, and it's very likely to cause the correlated failure across the entire network. Actually, sometimes that really happened. But I cannot expose the real outages here. And power source is another one. So the power source typically support a lot of components. Say, the two power sources support the thousands of routers or thousands of servers. And if the power source, some problems happen in power source, is also the dangerous. And we also need to use our system to audit whether some common dependency power source is introduced. In the network area, it's also common. For example, the aggregation switch and Tor switch that happen sometimes lead to the correlated failures across the entire network. And so actually we detected a lot of such dangerous common dependencies, and we found them on time, and this can solve a lot of problems from our network. So the RAP audit is the first system that use the SAS solver to finish the efficient audit for the correlated failure. And Cloud Canary actually is the first system we use them in the real world, and to audit the real time update. And so actually we also evaluate the Cloud Canary in the real world data, and like what I just showed. So this part is just a talk about one concrete example about how can we apply the SAS solver in the both academia and industry to build a real system. So in the end of my talk, I would tell you in the network analysis domain, what type of systems we can build to based on the SAT or SMT solver. And I also want to thank Nikolai. And so we actually, after I joined Alibaba, I widely used the SMT solver to build a lot of verification system in our network. So here I want to show this. I'm sorry. Yeah.
Anand, there's another question by Karam.
Yeah.
So the updates are incremental. Is the SAT solving also incremental? The SAT solver that's used in Cloud Canary, is that leveraging?
So we actually do not use the incremental thing for the SAT solver. We just use the algorithm to analyze, to extract the incremental part and directly use the original SAT solver to analyze the incremental part.
Thank you.
No, thanks. So because I'm not quite the SAS solver guy, so I really want to do some smart thing in the SAS solver, but unfortunately I didn't do that. So what I can do is to design an algorithm to extract the incremental part and use the original SAS solver to analyze it. So this is what I did. Yeah. Okay. Anyway. Yeah. So
maybe also to tell you, when we were using SAT solver, I think we were using we went to competition, found the fastest SAT solver that was publicly available, right? The one which was open source, right? So that's like it's not based on a smart insights and techniques. So that's why I thought it's really great that Anand is giving a talk so that you can kind of provide so much more feedback and bring more tools that we could use.
Yeah, exactly. Yeah. What we did is just to take a look at the ranking list about the SAS solver competition and just select one we can use and to apply that in our system. This is what we did.
Which solver is that?
We use Super Mario or
it was something that ends with Eno.
Maxino
right.
said, yeah, Maxino said, and also we also use the motor counter from the CUDI, that's the motor counter part for the failure probability computation presented by Ruzica. Yeah.
Okay. Thank you.
Thanks. Okay, so so this picture is just I want to show a big picture about the state of the art that apply the SAS solver and SMT solver in formal network analysis. I actually classify them into 3 groups: the rigorous network analysis, and verification and network synthesis. I guess you guys are super familiar with these 3 domains. And this is actually what I'm exactly working on in Alibaba. And so the first type is the rigorous checking, for the network. And in this scenario, typically the operator expresses their specification, say in first order logic, and convey the specification to the system, and the system automatically analyzes the target network. And the key challenge here is how to model the network or how to extract a reasonable network abstraction from the underneath. And so some existing work has been proposed. For example, like what just Ruzica talked about, the rep audit and index belong to this domain. And we also have we also observe another work from Microsoft. They use the software to check and test the configuration for the software. So the second domain is the formal network checking. So actually, the network configuration is a big problem, and the operators typically made a lot of wrong things in the configuration. But the configuration is the key thing for the network. They generate the routing table. They control the forwarding behaviors of the network. And so using the SMT solver in the network verification is a very, very important direction in the network and system area. And so in this domain, actually, the operator expressed the specification about the correctness of the network. For example, the reachability. I want router can talk with the router. I want router 1 can talk with router 2 in the in this path. And so I just want to check whether the routing table is correct. And here the challenge is how can we correctly express our intent and the network model, whether the network model is represented correctly. And another important thing is we want to use the SMT solver to check whether the network model meets our specification, right? And so typically in practice, we found the verification algorithm is slow, and whether we can speed up the SMT solver to to speed up this process. And so a lot of state-of-the-art proposed in the past years. For example, in data plane verification, we know the Veriflow and NOD. NOD is also the Nikolai's work and very much like this work. Yeah, and the control plane verification include the Minesweeper and the ERP. I strongly suggest you guys read the papers. And in our system and network community, we really want to have the super fast SMT solver to speed up the existing system. So in the network synthesis area, the operator typically express the specification. And in this case, we do not have any configuration for our network. And writing the configuration is very, very hard. So we want to just propose some synthesis algorithm, and this algorithm can generate the network configuration based on the spec. And in this area, of course, the challenge is how can we express the intent and what should be the synthesis algorithm. And the state-of-the-art include the configuration repair, and say the FireMason. FireMason was another collaboration between Ruzica and me and her student to automatically repair the firewall, and also the configuration synthesis, and including the CNIT net complete, like shown in this picture. And what I want to emphasize is, so all the all the work I just talked about focused on in the academia area, but whether we could build something in the industry to verify the global scale deployment. Actually, the Cloud Canary is one instance for the the global scale deployment. And for the network verification and the network synthesis, we have a gap, and we need a lot of work in this part. So after I joined Alibaba, actually we built a system named Huoyan, which can use SMT solver to verify the configuration. And of course, in Microsoft research, and Nikolai had a team to build another data plane verification system, published in SIGCOMM 2 years ago, I think. Yeah, I remember. Okay, so I think both of the systems prove that the SMT solver could be absolutely applied in the industry and to do the real, the real world verification for the network. This is an important thing. And in the network synthesis area, so I also built another system in Alibaba to synthesize the ACL rules for our network. And because this ACL rule is different from the firewall, because this ACL is the in-network ACL, because we have a lot of switches, and on each switch we have different ACLs, and this is so all the ACLs on different nodes work together to coordinate, control the reachability, and this is very challenging to generate the ACL for this distributed setting. So again, the picture shows a lot of state of the art, but all of them apply the SMT solver to enable the verification. And so thank you very much for the community. And what we need in the future is the faster SMT solver and SAS solver and more functions, say like the incremental speed up or something. Yeah, and we are very happy to use some the interesting SMT solver or SAS solver to speed up our checking and verification. So again, this is the end of my talk. So in this talk, we talked about some application for the existing SAS solver and SMT solver in the real world, and I'm happy to take any questions. Thank you.
Can I say something?
Yeah.
This is really cool. I like the application.
Thanks.
I think we need to see more applications of this technology, so that the secret about what we can do is not a secret anymore. That other communities can actually become familiar with it, and they can start using it. I think as a SAT community, we have not done as much, and we're kind of reaching out to other communities to show them that what we can do. So I'm standing on a soapbox over it. This talk about because about the application of technology that has been around now for 20-some years.
Vijay, you're mute. We can't hear you. Vijay.
Thank you, Karim. Nikolai, please go ahead.
Thank you. So very nice.
Hello. It's I cannot hear.
I'm getting a echo somehow. Not sure what's.
Albert, maybe you want to.
There's lots of echo.
Yeah, Albert.
Okay, so the echo seems to be gone, and I guess you can hear me.
Yeah, Nikolai,
Yes.
we can hear you.
So for the risk group enumeration, so you enumerate top risk groups and then check whether you have certain guarantees under top risk groups. Okay. So the question is, is there a formulation using quantifiers? Are you solving a problem there? Exists some configuration such that under all risk groups under certain some property. So if you had this quantified formulation, you could ask to the SAT community, what are the clever ways of solving this quantifier? And so one method that so I think colleagues in the networking space are using is employing linear programming dualities when there's a subset that exhibits strong dualities. So maybe in the SAT space, there are some other, there's a variant of this, and I wonder if you can you use your work to inspire the SAT community around this question.
Shall we? So
yeah, Ruzica, go ahead.
Reason why Anand and I look at each other, there is some sorts of quantification that I didn't present, and that was in the form of synthesis. If in the quantification doesn't exist in the language as we have, and also our synthesis is it's relatively simple and primitive, because what we did was you would more practically say whether there exists deployment such that, let's say failure probability of deployment falls under, I don't know, 0.20%. And that we can show that there is this quantification, that is whether there exists deployment. But what we do is we are solving this more or less on demand, in the sense that we are constructing the tree, and as soon that we see the tree is violating the constraints, we prune those branches. So it's not, like it is, if you look at the description of the algorithm, it's pretty much, like build a tree, does it violate, cut it away, build, continue, this prune away, that's it.
That's obviously very reasonable. And then the question is whether does it scale under, say, how does it scale with the sizes of networks, and then so the number of fault group combinations, right? So if you look for pairwise or triple.
Do you remember, Renan? I don't really recall. Maybe do you remember?
I I cannot remember that. It's so in the real world data we didn't use that, but in for the rep audit, I think the scale is, I think what, let me see, 10,000, I guess. We have 10,000 components, and we can synthesize within just several minutes.
Mm, yes.
But I guess Nikolai's question might be talked about in when we want to identify risk groups, whether we take into account the quantifier or something, right? Nikolai, is that your question actually is?
So of course there are very different. In your last slide you had the different categories of synthesizing a network configuration.
Yeah.
One or and depending on which line you're in, you have a different kind of problem you're checking, and then maybe it's in the last line where the query is, find a fixed configuration such that.
Yes, I see your point. Yeah, got it.
And to solve that, you can't just prune one branch at a time. You want to find the fixed configuration such that for all branches. And depending on
we did take into account that the quantifiers, like what you mentioned in the Hoi system. But yeah, what I think Ruzica just talked about is the cloud canary. There are the different system, but in our configuration verification, we did consider that. And because sometimes we want to check whether a specific configuration rule has some problem, or whether the reachability goes through from a specific path, including the specified component or switches. In that case, we did consider that thing in the Hoi system, which is the configuration verification system.
Right. Now, but the whole question is how to inspire the SAT community, and I believe that there's one angle that says whether it's say metric, some QBF with probabilities or weights or otherwise, and compile it into say small formulas, or solve these formulas.
I was going to echo the same point, Nikolai. If you can get a benchmark suite of instances from Ruzica and Inan, that would be fantastic, I think. So that would encourage the SAT community to be more engaged in. Here is a set of 100 challenge problems, for example.
But I think there's also theoretical. I think.
Exactly. Yeah. No, totally.
Anyway, so thank you.
Can we hope to get benchmarks, Ruzica and Inan?
Inan is there. He disappeared. So benchmarks from Uppsala, that's the one that I was presenting, are definitely available. I don't know for Alibaba benchmarks, are they a lot? I mean, are they? It's kind of shame. I will talk to Inan if
Sure.
Alibaba benchmarks are available, or even if they can be anonymized somehow. I will definitely encourage him to submit and to contact you. I mean, now you know each other, so that's
Totally,
the most important thing, right?
Yeah, absolutely.
Yeah. Okay,
thank you for a
just
fantastic talk, Inan and Ruzica.
Because he wouldn't even tell you how many nodes there are other than 20. So I think they're going to be very protective of their benchmark.
Mm-hmm. Yeah,
Because
Enan, I know that you're crashed, so I'm putting Enan on the speaker. Sorry about that's why I'm answering, because Enan is calling me to tell me that he crashed.
Okay.
Right. So I think the internet in my home was crashed because some guys outside are building
Yeah.
the subway or something. Sorry for that. Can you answer the questions instead of me? Sorry.
Yeah. No, Enan, the question was just. Are your benchmarks the ones that were in your follow-up systems, will they be publicly available or are they already publicly available?
What is publicly available?
You know,
data
like
or system?
The data. Benchmarks.
Data is not because our company do not allow that.
Mm-hmm. So the answer is that he cannot, because company doesn't, a system is available if I understood properly, but not the benchmarks. But our
right. So the rep audit is available. Rep audit passed the artifact evaluation, right? Because it's totally open source. You can ask them to use that, but Cloud Canary and the system I built in Alibaba is not available.
Okay. Thank you.
All right. Thanks again. Thanks.
Sorry to everybody. I'm really sorry.
Don't worry. Yeah. Okay. Thank you.
They are building something outside. They are building the subway for the random.
Yeah. Don't worry. It happens. Now we show that networks really can be unreliable. Thank you.
Okay.
Bye.
Sorry.
Bye.
So thank you, everybody. Thank you for the great speakers. So we are ending this session today. And I believe, Albert, there is going to be a gather town, or I think there was some kind of a seminar at 2, I think, by the
I'm not sure about this, to tell the truth.
By the mentees.
Yeah, maybe can I also say as an organizer of the other workshop, so on Monday we are starting with our seminar, our workshop, which will be on software synthesis, and we will have exciting very tutorial that given by Bernd Finkbeiner. So all of you who would like to know a little bit more, I mean, you're set people, you're using Booleans. You want to learn more about how to use them in the synthesis, please come on Monday for the synthesis workshop.
Okay, there is a comment by Sybil. The comment is, I would be particularly interested in benchmarks for model counting.
Mm-hmm. Okay, let me send this to Enan.
All right, Albert, is there anything else? Announcement of any sort?
Well, yeah, there's now the gather town is in link is in the chat.
Yeah.
So yeah, I just want to thank everybody for the great talks. So today it was nice to see we started with model counting and then we followed with SMT, and then the very last talk was putting both things together, right? So this was very
exactly.
nice.
Yeah.
So thank you very much for the great talks, and see you next time.
Yeah. Thank you, everybody. Bye-bye.
Bye-bye.
Bye-bye.